Welcome to the 7th lecture on the category of vector spaces titled Linear Independence. In this lecture, we are going to address one of the fundamental questions of linear algebra. Let's fix a vector space over a scalar field K. If A is a subset of our vector space, and V is a vector in the linear span of A, then we know that V is a linear combination of vectors in A. The key question here is this linear combination unique? Let's start with a simpler question. Let E and F be two subspaces of our vector space, and let's take an element omega in the sum of E and F. And let's write omega as U1 plus V1, where U1 is in E and V1 is in F. But let's also write omega as U2 plus V2, where U2 is in E and V2 is in F. And the question is, under what conditions do we have that U1 must be equal to U2 and V1 must be equal to V2? So really we are asking a question about the injectivity of a particular linear map. Namely, let's fix our vector space and two subspaces E and F in that vector space. We're going to define a map sigma which to an ordered pair VW in the Cartesian product of E with F maps the sum V plus W as a vector in our original vector space. This is obviously a linear map, as can be checked very easily from the product vector space E Cartesian product with F to the original vector space in which E and F live. And what we can see is that we can easily characterize when this map is injective, surjective, and therefore when it is a linear isomorphism. Sigma is surjective if and only if the sum of E and F is the entire vector space, and sigma is injective if and only if the intersection of E and F is reduced to the singleton 0. Now first, the range of the map sigma is by definition the sum of E and F. Therefore, the map sigma is surjective if and only if the sum equals the entire vector space. On the other hand, sigma is a linear map, so we have a characterization of its injectivity. Sigma is an injective linear map if and only if its kernel is reduced to the singleton 0. So I'm going to calculate the kernel of sigma now. Let VW be an element of the kernel of sigma. Remember that by construction, that means VW is an ordered pair in the Cartesian product E times F. Now, since I'm in the kernel of sigma, it means that 0 equals sigma applied to VW. In other words, 0 is equal to the sum of V and W. By adding minus W to this equation on both sides, we conclude that V equals minus W. And now W is an element of F by definition, so minus W is an element of F since F is a subspace, and therefore V, being equal to minus W, is also an element of F. But by construction, V is an element of E, therefore we must conclude that V is in the intersection between E and F. That being the case, W, which is equal to minus V, is also in the intersection of E and F, since E can intersect F is a subspace, so if it contains V, it contains minus V. So the kernel of our map is entirely contained in this set here, which is made of the Cartesian pairs of the form V minus V for V ranging over the intersection of E intersect F. That's what I have just shown. But on the other hand, it's very easy to check that if you take something of the form V minus V for V in the intersection of E and F, and you apply sigma to that, you get 0, since you add them up. So we have shown, in fact, the double inclusion that the kernel of my map sigma equals to that subspace of the ordered pair of the form V minus V in the Cartesian product E times F, where V ranges over the intersection of E and F. So again, when is sigma injective? Well, sigma is injective if and only if that subspace is a singleton 0. And how does that happen? Well, that happens, the only possible V you can possibly plug here is 0. So that forces the intersection of E intersect F to be the singleton 0. So we've shown our two conditions, our two equivalences, and note that in particular, sigma is a linear isomorphism between our vector space and the product E times F, if and only if it satisfies both these conditions. So I'm going to give a name to that very important situation. So if I have a vector space that I can write as the sum of two of its subspaces, but those two subspaces intersect only at the singleton 0, then I'm going to say that my vector space is the direct sum of those two subspaces. And I write it a little bit differently. Instead of plus, I write a plus with a circle around it. So it's a little bit of an interesting notation because actually, as far as what set the direct sum or the sum are, they're the same set. What writing this little circle around the addition symbol tells me is an extra piece of information. Not only am I calculating the sum of two subspaces, but I know that those two subspaces only intersect at the singleton 0. So keeping with the notation of our theorem, we see that basically our vector space is a direct sum of two of its subspaces if and only if the associated sigma map written in the theorem is a linear isomorphism. So the relevance of this definition is that it answers the easy question we stated in the introduction. Indeed, first let's say that our vector space is indeed the direct sum of two subspaces E and F. And let's say that we have two vectors v and v prime in E and two vectors w and w prime in F, subject to the relation that v plus w equals to v prime plus w prime. So in other words, using the notation of our theorem again, sigma of vw equals sigma of v prime w prime. Now the direct sum hypothesis here tells me that sigma is injective. So in particular, v equals v prime and w equals w prime. Conversely, let's say now that our vector space is just the sum of two subspaces, not necessarily a direct sum, just the sum a priori of two vector spaces E and F, but we add another condition, and the condition is that if you pick a vector in E plus F, you can only write it as a sum of an element of E and an element of F in a unique way, which mathematically is written in this slightly more awkward way. It says that if you take an arbitrary pair v and v prime in E and an arbitrary pair w prime in F, then v plus w equals v prime plus w prime if and only if v equals v prime and w equals w prime. So that's the condition if you look at it carefully, which tells you there's only one way you can possibly write a vector that is in the sum of E plus F as a sum of a vector in E and a vector in F. Under this unique decomposition condition, then we can conclude that the map sigma of the theorem, again, it has to be injective and surjective. Surjectivity is given because the vector space is the sum of E and F, but injectivity is built in right there. You see what we're saying, this complicated condition is saying that for any pair VW in the Cartesian product E with F and any other pair V prime W prime in the Cartesian product of E with F, if sigma of VW equals sigma of V prime W prime, then in fact VW equals V prime W prime. So that's exactly saying that sigma is injective, and of course when sigma is injective, we get the conditions stated in the theorem that tell us that our two subspaces E and F are in fact in direct sum, that is their intersection is reduced to singleton 0 and their sum is a whole space. If you look at the proof, I invite you to do that. We'll get back to it anyway in this lecture, but it is interesting to already notice this, what I call unique decomposition property for a sum of subspaces, that is this long property I just discussed, is also equivalent to what already look a lot simpler, the property that if you have a vector in E and a vector in F and their sum is 0, then it must be equivalent to both of those vectors to already be 0. So having two subspaces in direct sum position, that is the intersection is 0, means that if you take a vector in one and a vector in the other and you add them up and you get the answer 0, the only possible solution here is that you already picked the 0 vector in both of those vector spaces. So these are the sort of properties we're going to get familiar with in this lecture. Now I am going to generalize this concept of direct sum to finitely many spaces. So you fix your vector space and you give yourself n subspaces, E1, E2, etc., En, of your vector space. And just as before, I'm going to define a map sigma, which to n tuple of the form V1, V2, etc., Vn, where V1 is in E1, V2 is in E2, etc., Vn is in En, and map the sum V1 plus etc. plus Vn. Suddenly, if n equals 2, we recover the situation we had in the previous slide. And we have the following characterization of surjectivity and injectivity for sigma. Sigma is surjective if and only if the vector space is the sum of all of the subspaces E1, E2, etc., En. And it is injective if and only if we have this interesting property here, which says the following. First of all, you want E2 intersect E1 to be the singleton 0. But then you also want E3 to intersect the sum of E1 and E2 only at 0. And then you want E4 intersect with the sum of E3, E2, and E1 to only be 0. And the pattern thus continues until n. Now, there are actually counterexamples that show that this condition here is stronger than simply asking that if you take any two distinct indices I and j, that EI intersect EJ is a singleton 0. So whenever those two conditions are met, that is whenever sigma is a linear isomorphism, then you can again write your vector space as the direct sum of E1, E2, etc., En, and again you use this little plus symbol with a circle around it. So let's prove this result. We're going to do that in several steps. So let's first prove that if sigma is injective, then for any integer k between 2 and n, the intersection of the subspace ek with the sum E1 plus E2 plus etc. plus ek minus 1 is a singleton 0. So if we assume that sigma is injective, since sigma is also linear, we can conclude the kernel of sigma is a singleton 0. Fix k an integer between 2 and n. And let V be a vector in the intersection of the subspace ek with the sum E1 plus E2 etc. plus ek minus 1. In particular, V belongs to that sum, so there exists a V1 in E1, a V2 in E2, etc., a Vk minus 1 in ek minus 1, such that V is the sum V1 plus V2 plus etc. plus Vk minus 1. Now I want to relate this decomposition of V to the kernel of sigma. So to do that, I'm going to introduce a new vector, W, in the following way. W is in the domain of sigma, so it has n components, W1, etc., Wn, with W1 in E1, W2 in E2, etc., Wn in En. And for j between 1 and n, I decide that Wj is V sub j if j is between 1 and k minus 1, so one of the terms in the decomposition of V. Wj is minus V is if j equals k. Note that V is in ek, so that's well defined. That's appropriate to make this choice. Because V is in ek, therefore minus V is in ek, since ek is a subspace. And 0 for the coordinates past k. So what do I know about sigma of W? Well, it's the sum of all of its coordinates. So it's V1 plus V2 plus V3, etc. plus Vk minus 1 minus V, and then a bunch of zeros. But the sum of V1 plus V2, etc. plus Vk minus 1 is V, so you end up with V minus V, which is 0. What does that tell me? It tells me this W is in the kernel of sigma. What does that mean? It means W is a 0 vector, because sigma is injective. But among the coordinates of this vector W, we have the coordinate of index k, which is minus V. So minus V must be 0, and therefore V must be 0. So indeed, we've shown that the intersection of the subspace ek with the sum E1 plus E2, etc. plus ek minus 1, that must be contained in the singleton 0. Any element in there is 0, if there is any. But there is, of course, the vector 0 in that intersection, because it is in fact a subspace, as an intersection of two subspaces. And therefore, we have concluded our lemma. Now let's prove the converse of our previous lemma. So we assume that for any integer k between 2 and n, ek intersect the sum E1 plus E2 plus etc. plus ek minus 1 is reduced to a singleton 0. We want to show that the map sigma is an injective linear map. So let V be an element of the kernel of sigma. So it's an n tuple of the form V1 in V1, V2 in V2, etc., Vn in Vn. And my goal is to prove that V is 0, because that would indeed show that sigma, being a linear map, would be injective. I'm going to do reasoning by contradiction here. I'm going to assume V is not 0. So if v is not 0, that means that there is at least one of those v1, v2, etc., vn, which is not 0. What I'm going to do is I'm going to take the max index where I can find a non-zero vector in v. So for instance, if v is a non-zero vector followed by non-zero vectors and a 0, then a non-zero vector, and then a bunch of zeros, then m would be 4. So we're going to prove that something goes wrong no matter what m is. So let's say first that m equals 1. So what does that mean? It means that the max index where we have a non-zero entry in v is 1. So v2, v3, v4, etc., vn, they must all be 0 by definition of m. Then you can calculate what sigma v is easily, because remember, sigma simply adds the components of v, so sigma v is equal to v1. Everything else is 0. But v was chosen in the kernel of sigma, so that means that v1 must be 0. And that's a contradiction, because then all the entries of v, v1, and then v2, v3, etc., would be 0. And I just assume that v is not the 0 vector. So assume now that m is strictly more than 1. So then what do we know? Well, again, we know that sigma v must be 0, because v is in the kernel of sigma. So we can write what it means. It means that v1 plus etc. plus vm is 0, because past vm, by definition of m, all the other vectors are 0 in the m tuple v. So take the last one, vm, which is not 0. That's equal to minus the sum of v1 plus etc. plus vm minus 1. I just simply solve this little equation here. But what does that tell me? It tells me something interesting. On the one hand, vm, by definition of the domain of sigma, is in em, the subspace em. But on the other hand, v1 is in the subspace e1, v2 is in the subspace e2, etc. vm minus 1 is in the subspace em minus 1. So this sum here is in the subspace sum e1 plus e2 plus etc. plus em. And so minus of it is also there. So you see, we have shown that vm is at once in em and in the sum e1 plus e2 plus etc. plus em minus 1. And my assumption tells me that this intersection of these two spaces is a singleton 0, so vm must be 0. But that's a contradiction by the choice of m. If you look at the definition of m, in particular, vm should be non-zero, and I've just shown that it is in fact 0. So nothing works, no possible values of m between 1 and n is allowable, so in fact v must indeed be 0, and therefore my linear map sigma must be injective. So we have a characterization of the injectivity of the linear map sigma in terms of intersection of subspaces. So injectivity is immediate. I mean, it is simply obvious by definition of sigma that the range of sigma is the sum of the subspaces e1, e2, etc. to en, and therefore we're surjective if and only if this sum is the entire space. Now let's prove the following core result, which is the essence of what we are trying to achieve in this lecture. It concerns the unique decomposition of a vector along a direct sum. So let e1, e2, etc. en be subspaces of some vector space, such that that vector space is indeed the sum of e1, e2, etc. en. The following assertions are equivalent. First of all, this map sigma we have studied, which to an n-tuple of the form v1, v2, etc. vn, with v1 in e1, v2 in e2, etc., maps the sum v1 plus v2 plus etc. plus vn, is injective. Second of all, for all integer k between 2 and n, the intersection of the subspace ek with the sum e1 plus e2, etc. plus ek minus 1 is always a singleton 0, or in other words, the vector space is not just the sum e1 plus e2 plus en, but actually the direct sum of e1 with e2, etc. with en. If omega is any vector, then there exists a unique n-tuple v1, v2, etc. vn with v1 in e1, v2 in v2, etc. vn in en, such that omega equals v1 plus v2 plus v3, etc. plus vn. I emphasize here, very important, that this is for a unique n-tuple. And fourth, if 0 is equal to v1 plus etc. plus vn with v1 in e1, v2 in e2, etc. vn in en, then in fact v1 equals v2 equals v3 equals etc. equals vn equals 0. So let's prove this core result. It's basically entirely based on what we've done so far. It's a summary of our efforts. Indeed, the first two statements are equivalent by the previous theorem, which we just finished proving. Now, the third point is actually just a statement of the definition of what sigma being injective means. You see, if sigma is injective, then indeed there is only one possible way. You can write a vector of your vector space as the image by sigma of some n-tuple with the property again that the first coordinate of the n-tuple is in E1, the second in E2, etc. So certainly 3 is equivalent to 1 by definition. However, 3 is what we were seeking. This is the property we wanted to solve. When is it possible to write a vector in a unique way as a sum of vectors chosen in certain specific subspaces? And then the fourth point is maybe even more interesting for the purpose of this discussion. The way you deduce the fourth point is by applying the third to the special case omega equals 0. It tells you there's only one way you can write 0 as v1 plus v2 plus etc. plus vn, with v1 in e1, v2 in e2, etc. But we actually know that way, because we can simply choose v1 equals v2 equal etc. equal vn equals 0. So 3 implies 4. It's the only way we can write 0 if 3 is true. On the other hand, 4 implies 1 because, in fact, what 4 tells us is something about the kernel of sigma. If you take an n-tuple v1, v2, etc., vn, with v1 in e1, v2 in e2, etc., in other words, an n-tuple in the domain of sigma, then when you apply sigma to that n-tuple, if that n-tuple is in the kernel of sigma, then you get 0. But what does it mean to apply sigma to that n-tuple? It means you're calculating v1 plus v2 plus vn. So, such an n-tuple is in the kernel of sigma if and only if v1 plus v2 plus etc. plus vn is 0, which by the point 4 means that v1, v2, v3, etc. are all 0. So in summary, the kernel of sigma is reduced to a singleton 0. That's all there is in there. And therefore sigma as a linear map with a kernel reduced to the singleton 0 must be injective. And so we looped. We get our equivalence. But I want to emphasize something here. Property 3 is kind of what we wanted. We want this unique decomposition property. Property 4 tells us that the unique decomposition property holds, but only for one vector, namely the vector 0. And remarkably, after our efforts, we've seen that 3 and 4 are equivalent. They're also equivalent to these other properties listed above, and it's interesting that in fact what we've shown, it's a corollary of this, is that if ever you have a vector space that's a direct sum of E1 with E2, with E3, etc. with En, then your vector space is actually isomorphic, linearly isomorphic to the product of E1 with E2, with etc. with En. So if you remember, if you go back to our lectures, we proved fairly early on that product of vector spaces were vector spaces. And now we see that basically what decomposing a vector space in a direct sum means is finding that this vector space is isomorphic to a particular product. So on with all this understanding, we can now actually introduce the most important concept of this lecture and of really many lectures. It's a core concept of linear algebra, and it's called linear independence. So here's the idea. You have a vector space and you take n non-zero vectors in your vector space, v1, v2, etc., vn. And I claim the following two conditions are equivalent. The first condition is that my vector space is actually the direct sum of the span of v1 with the span of v2, with the span of v3, etc., with the span of vn. So you can write your vector space in this very particular direct sum decomposition. The second assertion says that, first of all, the vector space is the span of v1, v2, etc., vn. And second of all, it has these funny properties that if you write a linear combination of v1 and etc. vn, which equals to 0, then the coefficients of that linear combination must have been 0 to begin with. That's what this statement that is written here formally tells you. So formally what it says is, if t1, t2, etc., tn are scalars, And if T1 V1 plus T2 V2 plus etc. plus Tn Vn equals 0, then T1 equals T2 equals T3 etc. equals Tn equals 0. So I'm going to prove this very important theorem, and what I'm going to do is highlight what I'm assuming and prove what is not highlighted. So first I'm assuming that my vector space is indeed written as a direct sum of the span of V1 with the span of V2, etc. with the span of Vn. So in particular, my vector space is in fact the sum of the span of V1 with the span of V2, etc. with the span of Vn, which means in other words that any vector can be written as a scalar multiple of V1 plus a scalar multiple of V2 plus etc. plus a scalar multiple of Vn. Or in other words, any vector can be written as a linear combination of the set V1 etc. Vn, so the vector space is indeed equal to the span of V1 etc. Vn. Now let's look at this interesting condition here. Well, alright, let's write 0 equals T1 V1 plus etc. plus Tn Vn for T1 etc. Tn scalars. By the theorem about unique decomposition I just did in the previous slide, since I'm assuming that here my vector space is a direct sum of those spans, I can conclude that each term in that particular sum must be 0. So T1 V1, T2 V2, etc., Tn Vn are all 0. But for convenience, I assume that V1, V2, etc. vectors are non-zero, so that forces the scalar T1, T2, etc. Tn to be 0. And I have shown that 2 actually holds. Now let's assume 2. Alright, the first thing I'm going to observe here is that, well, if my vector space is a span of V1, etc. Vn, since span of unions are sum of spans, I can indeed conclude that my vector space is the sum of the span of V1 with the span of V2, etc. with the span of Vn. Now, on the other hand, let's try to prove that this is not just a sum, but a direct sum. And I'm going to again use my previous theorem, specifically the implication 4 implies 2 in my previous theorem. And so I'm going to give again an expression for 0. 0 equals a linear combination of V1 to Vn, so 0 equals T1 V1 plus etc. plus Tn Vn. But I know that if that ever happens, the condition in red tells me T1 equals etc. T equals Tn equals 0. So the only way I can write 0 as a sum of a vector from the span of V1, and then a vector from the span of V2, and then etc., and then a vector in the span of Vn, is by actually choosing 0 in each of those spans. And that's exactly the condition that ensures that the sum is indeed a direct sum. And so 1 holds. So, let's summarize. What's good about direct sums? What's good about a direct sum is there's a unique way to decompose a vector as a sum of terms, each of them in the summand of your direct sum. Okay? So that's a good thing, this uniqueness property. What is good about this red property is that it's a characterization of being a direct sum, which only involves the vector 0. It's a very explicit statement about what I need to check so that I can indeed conclude that my vector space is decomposable as stated. These very important red statements get abstracted into the following definition that is really one of the very, very central concepts of linear algebra. So a subset A of a vector space is linearly independent when for all finite subset V1, V2, etc. Vn of A, and for all scalars T1, etc. Tn, if the linear combination T1 V1 plus T2 V2 etc. plus Tn Vn is 0, then the scalars T1, T2 etc. Tn must all be 0. This is of course very much inspired by assertion 2 in the previous theorem. We now have worked hard to see where such a definition could possibly come from. It comes from this idea of direct sum and unique decomposition. So this is a technical definition. You need to spend some time realizing what it says. It says that to prove that a finite set, say v1, vn, is linearly independent in particular, what you need to do is you have to take an arbitrary linear combination of those vectors and somehow show that if that linear combination is 0, then the coefficients must be 0. You have to solve this problem. Let's make some observations about this. So first of all, I'm going to observe that if the 0 vector is inside your subset A, then A has no chance of being linearly independent. And that's because the vector 0, you can scale it by anything you want, and it still gives you 0. So in particular, you can scale it by 1, for instance. So 1 times 0 equals 0. Okay? So that's a linear combination where at least one of the coefficients is not null, because it's 1, and yet it still gives you 0. So it contradicts linear independence. So that's the first thing that is important to realize. When you're talking about linear independent subset, they cannot contain 0. On the other hand, maybe a bit surprisingly, but it's one of those funny consequences of some of the assumptions we made about logical connectors in mathematics, the empty set is actually linearly independent because, well, the statement is vacuous for the empty set. So it is linearly independent by vacuousness, so to speak. Then the next easy case is to look at a singleton. So if your subset A is just a single vector, under what condition is a singleton linearly independent? And that's very easy. The condition is actually the only one that can be, that is, a vector is not 0. We just saw if 0 was in the singleton, then of course it's not linearly independent. That's the only constraint. If you have a non-zero vector, what happens is if you multiply that vector by scalar t and you get 0, we know that either t is 0 or the vector is 0, but since we assume the vector is not 0, we get t equals 0. And so we have indeed shown the only way I can do a linear combination of a singleton v, where v is a non-zero vector, to get 0 is by multiplying my vector by 0. And so, by definition, the singleton is then linearly independent. So now I'm going to make a couple of quick observations that will prove helpful for my next remark about linear independence. So look at this very simple map. You take a vector v and you define the map that goes to the scalar field into the vector space, which to a scalar t maps t times v. When is this injective? That's injective exactly when v is not 0, as can be checked very easily. And this can be generalized. More generally, if you give me n vectors, v1, v2, etc., vn, and you define this map written here that two scalars t1, t2, etc., tn maps this n tuple t1 times v1, comma t2 times v2, etc., tn times vn, just the n tuple here. This map is injective exactly when none of the vectors v1, v2, etc., vn has 0. Very, very simple observation. So here is a bunch of simple linear injective maps. And why this is useful is because if I compose them with these sigma maps I've been talking about on the previous slides, I can then deduce the following result. That if you take a finite subset of a vector space, v1, v2, etc., vn, this finite subset is linearly independent when the linear map, which to n scalars t1, t2, etc., tn maps the linear combination t1, v1 plus t2, v2, etc. plus tn, vn is injective. So a consequence of that is that the definition in the blue box of linear independence implies, or it actually is equivalent in that case, to the statement that if you have two linear combinations of the same vector v1 to vn, and it happens that v1 to vn is linearly independent, then in fact the coefficients in those two linear combinations must actually be equal. And this blue box at the bottom in turn implies that the family v1 to vn is linearly independent, right? Because simply apply it to the special case where all the s here are 0, and you get exactly the statement of the definition. So when you want to understand a concept, it is often useful to try and understand its contradiction as well. So the contradiction of linear independence is called linear dependence. So again, let's fix a vector space and let A be a subset of that vector space. The first statement here says that if you take omega, a vector in the linear span of A, then the set A union the singleton omega is linearly dependent. So another way to state this is you give me a set, and in that set there is a vector, which is a linear combination of other vectors of that same set. Then that set is not linearly independent, it is linearly dependent. Namely, there is a linear relations among the elements of that set. A non-trivial linear relation, because of course every vector is 1 times itself, but a non-trivial one where your vector is expressed as a linear combination of other vectors. So that's the essence of linear dependence, and therefore by contradiction you can understand a little more the essence of linear independence. Moreover, if your set A is linearly independent, and you pick an arbitrary vector omega such that when you form the union A with the singleton omega, suddenly the set becomes linearly dependent, then it means that in fact your omega vector is in the span of A. Okay? So that explains linear independence and linear dependence a little bit more. And let's prove these two statements. So first, suppose that you have omega in the span of some A. So what does that mean? Well, we've learned that it means omega is a linear combination of some vectors in A. So in other words, there exist scalars t1, t2, etc., tn, and vectors v1, v2, etc., vn in A, such that your omega is the linear combination t1, v1 plus t2, v2, etc., plus tn, vn. But then what I can do is, well, you take this equality and I add minus omega on both sides. But remember, minus omega is minus 1 times omega. So if you look at this, I have now a linear combination of vectors in the set A union singleton omega with at least one non-zero coefficient, namely minus 1. So, indeed, we conclude that the family omega, v1, etc., vn is linearly dependent. It's not linearly independent. And so, a fortiori, the larger set A union the singleton omega is linearly dependent. That proves our first bullet point. So let's prove the second point. So I'm assuming A is linearly independent, yet A union the singleton omega is now dependent, linearly dependent. So what does that mean to be linearly dependent? Well, it's the contradiction of the statement about linear independence. So it means I can write the vector 0 as linear combinations of vector in A union the singleton omega, but where not all the coefficients are null. That's what it means. That's the exact contradiction. So that's what I write here. You can find a bunch of scalar t1, t2, etc., tn, not all of them 0, and a bunch of vectors v1, etc., vn in A union the singleton omega, such that t1, v1 plus t2, v2 plus etc. plus tn, vn equals 0. And then I make a couple of observations. If the set v1, v2, etc., vn was a subset of A, then it would force all the scalars to be 0 because A is linearly independent. So if I was able to write 0 as a linear combination of v1, etc., vn, then the only way I was able to do that is by using the coefficient 0. But I assume my coefficients were all 0. So I must conclude that at least one of the vector v1, v2, etc., vn must be omega. Okay, because they can't all be inside A. And note that, by the way, omega cannot be in A either, because A is assumed linearly independent, and then when you throw omega inside, suddenly it becomes linearly dependent. So it wasn't there to begin with. So, without loss of generality here, it's just a naming convention. I'm going to just say v1, say, is omega, to make notations easy. And then the other observation, which is for the same reason, is that t1 cannot be 0 either, because if t1 was 0, then you multiply omega by 0. And then you're back to really doing a linear combination of vectors in A, which is equal to 0. And again, all the coefficients would have to be 0. And I assume that not all the coefficients are 0. So t1 cannot be 0. I must have omega with a non-trivial coefficient in that particular linear combination equal to 0 because of the linear independence of A. But then what I have is this linear combination t1w plus t2v2 plus t3v3 etc. plus tnvn equals 0. So I put, t1 times omega on the other side, and I divide by t1, which I can because t1 cannot be 0, and I get that omega is in fact this expression here. So it's minus t2 over t1 v2 minus t3 over t1 v3 etc. minus tn over t1 vn. And you recognize that I've written omega as the linear combinations of the vector v2, etc., vn. So I've written my omega as an element of the span of A, because v2, etc., vn must be in A. Remember, in a set, that's an important feature of set theory, right? When you're a least element of a set, you cannot repeat the same element twice. A set does not have sort of a multiplicity concept attached to it. So since we already know that we decided, one of the vectors is omega, well, all the other vectors must be in A. So this proves my second point here, okay? And we have to be careful. This is not hard, but there's a lot of little things to check. However, this gives us a very nice description of the idea of linear independence and its contradiction, linear dependence. As soon as a vector can be written as a linear combination of other vectors in a set, you lose linear independence. Linear independence, in other words, is really saying that your set is made of a bunch of vectors, none of which can be written as a linear combination of the others. That is exactly equivalent to linear independence, in fact. So I'm going to conclude this lecture with a result regarding the relation between linear maps and linear independence. Let V and W be two vector spaces, and phi a linear map between them. If you take A a subset of V, if phi restricted to A is injective, and if phi of A is linearly independent, then A was already linearly independent as well. Let's prove this result. Let's pick a subset of n vectors in A called v1 to vn and n scalars t1 to tn, such that t1 v1 plus t2 v2 plus etc. plus tn vn equals 0. Then by applying the linear map phi to this linear combination, we get that 0 is equal to phi applied to the sum from j equals 1 to n of tn vn. But by linearity of phi, that's the sum from j equals 1 to n of tn phi of vn. Now here we're going to use the fact that phi is injective to note that the set phi of v1, etc. phi of vn is indeed a set of n elements, which is properly denoted here. And it's important because then we can apply the fact that phi of A is linearly independent to conclude that t1, etc. tn are all equal to 0. This indeed proves that our set A is linearly independent as claimed. So we are now in good position to start discussing the notion of bases. A base is basically a spanning linearly independent family. But we'll see that this is tightly related to notions of minimality of spanning families, which we discussed when we talked about subspaces, maximality of linear independent families, and of course there's a question of whether bases actually exist in general. So in our next lecture, we will address those questions and we will introduce the notion of a finite dimensional vector space.